Yeah, we're happy to have Nima Hoda, who will give his first talk on superficial nonpositive curvature.
Thanks. Yeah, so I'll be giving a series of talks on notions of nonpositive curvature. Of course, our other mini course speakers will also be talking about notions of nonpositive curvature. So I'll be talking about other ones and their relations to group theory. And I'm going to start, sort of close to the beginning of this topic of combinatorial nonpositive curvature and group theory, and that's classical small cancellation theory. Okay, I can speak louder. Yeah. So I'm going to start talking about, I'm going to start with classical small cancellation theory. There are notes for this part online. So if you go to sc.nimahoda.net, you can get the notes, and also the exercises for the problem solving sessions are also in the notes. I'll mention some of the exercises during my lecture, but not maybe not all the ones that are there. Okay, so I don't want to assume any kind of knowledge, so I'm going to start by talking about two complexes and disk diagrams. Okay, so a two complex is a two-dimensional cell complex whose two cell attaching maps are combinatorial. What I mean by that is that if you look at the attaching maps of two cells, so if this is an attaching map of a two complex X, going to the one skeleton, then the attaching map is from a copy of S1 subdivided into segments, each of which maps onto an edge of X1, the underlying graph. And I think that'll be fully clarified by looking at a couple of examples. So say the underlying graph of our two complex could be something like this, let's say. And we could have the following two cells. And let's say another one. Okay. And so the space we're thinking about here has this as a subspace, and then we take each of these disks and we glue them to this graph along the map implied by the arrows along the boundary. Very important class of examples. Yes?
What's the two-cell complex?
It's an example of a thing like this.
Yes. Sorry.
What's a cell complex? In general, a cell complex is a kind of space that's built up inductively. In dimension 2, you start with a graph. Could have loops, could have multi-edges, and you glue disks to that graph along the boundary of the disks via maps from the boundary into the graph. Now, in the particular examples that we're looking at, those maps are all graph homomorphisms. I don't know if that language makes it better, but in this example, we take the disjoint union of this space, which is a graph, and these two disks, and then we take the quotient that identifies each directed and directed edge here with its marking, and we glue it to the appropriate edge of the graph with the same marking in the same orientation. Okay, a very important class of examples comes from group presentations. So a group presentation is given by some number of generators and some number of relators, which are words that are trivial. So this is a quotient of the free group generated by the GI. So any group presentation defines a two complex in the following manner. The one skeleton, the underlying graph, looks like this. We have a bouquet of circles. So it's a graph with a single vertex and as many loops as there are generators. And for each relator, we add a disk. Okay, and the disk is glued into the bouquet of circles along the word, the corresponding word. Okay. And so we'll look at another example here. A specific example of this. So if we take the standard presentation for z squared, that's going to be our one skeleton, and we have a single cell. And if we perform the gluing, we get the torus. Okay. All right, and it turns out that the fundamental group of the associated two complex is isomorphic to the group that's presented by the presentation. Essentially, by mapping each generator to the loop with its label. That's an important fact. I'll also mention that covering spaces of two complexes are also two complexes. So for example, the covering space of this guy is the standard square tiling of the plane. Any questions about two complexes? Should I continue here? Is that all right? Okay, so I'm going to define. What's that? Sure. A disk diagram D in S2 is a finite contractible two complex embedded in the two sphere. Okay. D is non-singular if it is homeomorphic to the two ball. Okay, so yeah, this diagrams feature heavily in small cancellation theory. Let's look at a few examples. There's one. That's the two complex with a single vertex and no edges and no two cells. Trees embedded in S2. We're going to view S2 as the plane with some point at infinity. These are also disk diagrams. Also have complicated things happening. We call these degree 1 vertices on the boundary spurs. And here's an example of a non-singular disk diagram. So this one's non-singular. All right. So except for the case where D is a single point, a combinatorial boundary path, I'll call it a boundary cycle. And you can think of that as the, you could add one more disk to this thing to get a two complex cellulation of the two sphere. So you could think of this boundary cycle as the attaching map of that two cell, or you could sort of just, that's sort of what the map does. Okay, so it's not the map is an isomorphism only in the case onto the boundary. That is, it's an embedding only in the case where the disk diagram is not singular. Questions about disk diagrams? These are sometimes called Van Kampen diagrams. Okay. Well, I mentioned combinatorial maps before, but I didn't define them in general. So let me do that now. A continuous map of two complexes, say X to Y, is combinatorial if it sends each open cell of X onto an open cell of Y homeomorphically. And a cycle C in the one skeleton is a combinatorial map from a subdivided copy of S1.
So when were you saying that you're talking about spurs as they cause things to be singular, or
There was no real comment. I mean, if you have a spur, you are singular.
Yeah.
But you could be singular without having spurs. All I really said was like these are what spurs are. So yeah, yeah. Degree 1 vertices on the boundary. Yeah. Yeah.
Here, X and Y are both two complexes.
Yes. Yeah. So I mean, yeah. When I say a map of two complexes, yeah, that's yeah. A continuous map of two complexes. Yes, they are two complexes. Yeah. Thank you. A map that collapses an edge to say a point is not combinatorial. That's right. Yeah. So yeah.
So it could also be singular if you like had an edge connecting two parts, or if they were actually just kind of connected at a vertex. Is
that would also be a singular diagram. So if you had something like that, yeah, that's singular. Okay, so why do we care about disk diagrams? Well, because they're everything. I mean, Van Kampen, yeah, according to Van Kampen's lemma, this is how you know what group you've got is disk diagrams. That's let X be a two complex. Let F from X to Y be a cycle if F is null homotopic, then there exists a disk diagram D, a combinatorial map from D to X, and a combinatorial isomorphism from C to the boundary of D, such that the following diagram commutes. the diagram is this one. There's our cycle in X. Okay.
When you first wrote F, should that be a method?
Yes, it really should. Thank you. So that's F, our cycle. We have an isomorphism, so essentially some identification between C and this orange boundary path of this diagram. That's our map from the boundary path into D. And that's the combinatorial map from D into X. Okay, and this commutes. So what that means is that this cycle is it's the composition. I mean, it's the composition of the inclusion of the boundary path of this not the inclusion, but the boundary path of this diagram, and then a map from this diagram into our complex. All right, and we say that this D to X is a disk diagram for F. The disk diagram in X for F. Okay, so let me give an example. Again, we take our standard torus, and let C to X be the cycle described by the word A to the 4, B, A inverse, B to the -3, A to the -2, B squared, A to the -1. So here's this diagram for this word, choosing a bad one on purpose. Okay, so there we go. That's our disk diagram. The map is described by the edge labelings, and because every two cell that we see in this disk diagram, its boundary label is the same as the two cell that we have. We know that this is a disk diagram in X. If you read the boundary word, you'll see that word. Okay, so then this is a disk diagram for that word. Is that right? A to the 4, A, B, A inverse, B inverse 3 times, A inverse twice, B twice, and then A. But yeah, you might notice that we could simplify this diagram and get one with less 2 cells, essentially by deleting this piece that we have over here. I'll draw that. We delete the insides, then we can glue. Now we have a gaping hole in the plane. But we can glue the plane, the sphere, back together again. And the end result is that we've replaced this part of the diagram. Yeah, I guess I'll erase it with just that. Okay. And that brings us to the definition of a foldable pair. Okay. Pair of 2 cells, R1 and R2 of a disk diagram D in X are foldable if they have a common edge E such that reading the boundary paths of R1 and R2 starting at E gives the same path in X, and I'll clarify that with a little drawing here. So we have some pair of two cells inside of our disk diagram D. Okay, and our disk diagram D is in X, so we have a combinatorial map to X. They have a common edge E, and if we were to read off the boundary paths starting from E in R2 and in R1, which we sort of, okay, we can consider these as maps into the disk diagram. And this is a foldable pair if these two coincide in X. So if we compose this path with the map to X, we get the same path as if we compose this path in here with the map to X. Okay, so that's a foldable pair. It's an important fact that if you have a foldable pair, you can always perform a surgery that deletes the two cells involved, R1 and R2, and and after some re-gluing, sewing the plane back up, we can obtain a disk diagram for the same cycle in X with fewer two cells. Okay, so you can. It's not entirely. It's maybe less obvious than you might imagine because these two might intersect in very complicated ways, but that's something you can think about. Any questions about Van Kampen's lemma or foldable pairs?
This diagram is on the right half of the board. Say we take the two bottom cells and the top and bottom A's on the right side.
Yeah.
We invert them.
Yeah.
Right. That would make that foldable, correct?
That's exactly correct. Yeah. I mean that would mean that would result in something that's not a disk diagram in X.
It wouldn't even be
but,
the same for
Right. But exactly. Yeah. That if that was a disk diagram somewhere, then it would have a foldable pair. Yeah. Any other questions? We're clear on this? Okay. So let me say what it means for a disk diagram to be reduced. Maybe that might be too hard to see, so I'll do that here. So a disk diagram in X is reduced if it has no foldable pairs. Okay, there's no obvious way to make it have less area so that you can just read off easily. So I'll make a remark here that if D is minimal area, by which we mean has least number of two cells among all disk diagrams for the same cycle. Okay, so we're ready now to start talking about classical small cancellation conditions. So we're, from now on, we're going to assume that our two cell attaching maps are immersed. So our two cells are immersed. What that means is that along the attaching map of a two cell, we would not see something like that. Okay, the two cell attaching maps are locally injective. Consider a reduced this diagram D to X, where D is the union of two cells whose intersection is a path of length at least one. So there's our path of length at least one. Here's our two cells. And this is the form of disk diagrams that we're interested in. So consider such a disk diagram that is reduced. A piece of X is the path P to X obtained by restricting this diagram D to X. Right. So if P can appear somewhere as the intersection of two cells in a reduced disk diagram, that's what it means for P to be a piece. Yes.
Does it have to be maximal in some sense, like you said, but that's right?
It doesn't. It doesn't. Yeah. I mean, so suppose we have some edge E over here. Well, then there's an equally good disk diagram of this sort that looks like this, where we slice this open from down here and then from up here, and yeah, this path of length one, given by restricting, is also a piece. Yeah. You give a few examples. So if X is the two complex coming from this presentation. Oh, I already got that one. Oops. Then AB and B squared are pieces. ABA is not. Yeah. Such D to X is a reduced disk diagram of this form. And restricting to P means restricting the map from this disk diagram into X into to P. Okay, so let's draw some disk diagrams that show why these guys are pieces. A, B, right? ABA, ABA. Okay, and then this also appears here as AB, A inverse, B inverse. Okay, so this shows that AB is a piece, right? Because AB appears along these two relators. We glue them together along the common word, we get a disk diagram that's reduced. B squared appears twice in this relator in essentially distinct ways. So we have the b squared that's over here, and we got some b squared that's inside this b cubed. Okay, so those are essentially unique ways that b squared appears. So b squared a b cubed a, as opposed to b squared coming from the b cubed a, and then b squared a. Okay, so this is reduced because if we start reading from here at the first step, we see that our words don't coincide, right? Whereas if we try to do the same thing with, oh, so I think that's probably not. Yeah, if we try to do the same thing with ABA, which appears twice in this relator, A, B, A. Even if we chose the two different copies of ABA that we have here and we glued along those ones, meaning that, you know, maybe this 2-cell kind of starts over here, and this one kind of starts over here, if you will. Well, that's not reduced. Okay, so we can't call that a piece, not for that reason. Okay, maybe, you know, maybe if we had some other 2-cell here, that could be used to prove that ABA is a piece, but we don't actually, not in this example. Yes.
Is there, and maybe I'm missing something, is there like a straightforward way of determining what the pieces are between a set of relators? Like suppose these were, you know, 6,000 characters long and you couldn't nicely draw them out. Is there some more straightforward way to see what the pieces of a set of relators are?
If you want an algorithm or something.
Does one exist? I get my question.
I mean, I don't know. I mean, I think I suspect yes. I haven't thought about that, but I suspect you could probably, I don't know, there's probably some data structure that can be constructed that can help you usually find the pieces. Yeah.
Okay. Fair enough. Yeah.
Does anyone know? Does anyone solve that?
Is it
Yeah.
the same notion that you take your relators
Yeah.
and take all the cyclic conjugates of them
Mhm.
and then check who has same prefix?
Cyclic conjugates and prefixes. Yeah. Yeah.
You make the list of all cyclic conjugates. I mean, in your
Yeah.
example, so ABA square, and you take the naive list, it will appear twice, but it's the same word.
Mhm.
So it's only one. So you have this list of all the cyclic conjugates of the words.
Yeah.
And then you check what are the prefixes.
But-
And that would make the list of pieces. Is that the same notion?
Yeah, that's the same notion. Yeah. I mean, so what?
Right. So
Yeah.
the answer appears to be no, there is not a straightforward. Because checking all like cyclic conjugates, you have to later. Only 6,000, right?
Yeah, but like, yeah. Yeah. If I were to guess right on the spot, I would say there's probably an efficient way to do that, but I'm not, you know,
I'm just curious.
I don't know, whatever. Yeah. Let's find that algorithm after.
Yeah.
Is there another question? Yeah.
This.
Will it depend on, it'll absolutely depend on the presentation. Yeah. Yes.
There's no maximality about what's stopping, say, this page from being used.
What's stopping A from being a piece? Oh, this is not an exhaustive list. A is absolutely a piece. Yeah. Good question.
So it looks like in order to determine that something is not a piece, well, in order to determine something is a piece, you have to find the right disk or a nice disk diagram that's not reduced, you know, show it. So if something is not a piece, it seems more difficult to show because you have to show that for any reduced disk diagram, like for any disk diagram, like you're not gonna reduce or something.
That's true. Yeah.
So it's kind of not. I mean, maybe it's the same kind of question. I don't know, but not immediately straightforward. So, like, show us something is not a piece.
Yep. Okay, so that's what a piece is in X. I'll also talk about pieces in the boundary of a relator. So the pieces of a two-cell R of X are the subpaths of its boundary cycle for which the composition piece of X. Yeah, I guess we don't need this exactly to be an embedding for my purposes, as long as it's an embedding, except at the endpoints. Okay. So the pieces of X give us some particular subpaths of the boundary cycle of any two cell. Okay, so why do we care about pieces? Define some small cancellation conditions. Let X be a two complex with immersed two cells. Let P be at least 3, and let Q be at least 3. X is C prime of one over, no, habit. C prime of 1 over P. If any piece P in the boundary of R of any two cell R of X has length strictly less than 1 over P times the total boundary length of R. Okay. So if you have such a reduced disk diagram in X, this common portion of the two cells is going to be short relative to the total length of either two cells boundary. Okay, so strictly less than a 1 over P proportion of the total length. Okay, so that's the C prime of 1 over P condition. X is C of P if for any piece in the boundary, no, that's not right. If for any two cell R, the boundary is the union of at most, of at least, is not, okay, is not the union of less than P pieces. Okay, so here's our two cell R, and certain subpaths are going to be pieces, and we insist that there's no collection of them of size less than P that covers all of the boundary. Q has not been used yet. Yeah, you might have to wait until next lecture for Q to be used. We'll see. But here's our first exercise, at least that I'm stating in the lecture. There are more in the notes. That C prime of 1 over P implies C of floor of P plus 1. But, well, let me say, in particular, C of P, but that the converse does not hold. Okay. And I think I'm out of time, right? Am I out of time? Yeah, okay. So we'll save the TQ condition for next time.
Just out of curiosity, given the boundary, and given the presentation, is the minimal disk,
No, no, yeah, very much no. Yeah, even in very nice cases, I think it's not.
Repeat the question and answer it. You can hear.
Yeah, the question was, is our minimal area disk diagrams unique? And the answer is no.
Exercise.
Exercise, yeah, that's a great exercise. Yeah, yeah.
Yes. Are reduced always going to be
No, no. That's another good exercise. Yeah. So we've got two great exercises. Prove reduced does not imply minimal area, and prove min area disk diagrams not unique. You're only going to get more homework. That's
Let's do Zoom at 12:06.